This video is about definite integrals, specifically using geometry to evaluate them and just some basic properties of definite integrals. So the first thing is remember that a definite integral, which looks like this with the integrand and a lower limit and an upper limit, and it represents sort of area under the curve, the definition of this is it's a limit of Riemann sums. So Riemann sums are a way to approximate area under the curve, and you take the limit as there's infinitely many rectangles which are infinitely thin, and that gives you a definite integral. But evaluating a limit of Riemann sums is pretty cumbersome. It's not exactly straightforward or clean, so we'd like a better way to evaluate definite integrals. And there is a generic better way, something called the fundamental theorem of calculus, which we'll get to in another video. But for now, we just want to talk about sort of using some geometry and some basic properties of what these things are. So let's start with the geometry ones. So use geometry to evaluate this definite integral, so negative 1 to 2 x dx. So let's just remind ourselves that this set of symbols is telling me if I think about the function x, right, it's a sort of standard diagonal, and I think about the interval ranging from negative 1 to 2, this set of symbols is asking me to calculate the area under the curve, specifically the signed area under the curve. So under the curve really means trapped between the curve and the axis. So this triangle is going to be some positive area. This triangle, because it's under the axis, is going to be negative area. So, I mean, using geometry, I know how to calculate areas of triangles. It's 1/2 base times height, right? So the positive triangle will be 1/2. The base is 2, the height is also 2, right, because this is the standard diagonal function. So this is 1/2 2 times 2, and then this area of this triangle is negative, so it's 1/2 1 times 1. So here I'm just leveraging up. I know this is area under the curve, and the areas represented here are triangles, so that's easy to calculate geometrically what their area is. So in this case, right, I end up with 2 minus 1/2, right, because this half and this 2 cancel out, or 3/2. Easy enough. Let's try another one. So again, now it's slightly more complex. This is also sort of linear, but we've got these absolute values in here as well. So let's just sketch this up. So you may need a refresher on graph transformations to think about how this one is going to look. 1 2 3 4 5. Okay, so this one, you can imagine if you want to think about how these absolute values should work, if you don't want to think about graph transformations necessarily, without the absolute value symbols, this should have a y-intercept of 3, right, and a slope of negative 1, which means it should be coming down like this. And normally it would continue this way, but I don't want to allow for negative values because I'm taking the absolute value, which means that these get reflected up. So if I'm taking the interval from 0 to 4, right, that means that I'm thinking about this area and this area. And because they're both above the axis, this is all positive, this is also positive. So this one again amounts to adding up a couple of triangles. So you could end up with rectangles if you have a constant function. You could end up with semicircles, you know, things like this. But these two examples were both just triangles. So for the big triangle, it's going to be 1/2, the base and height are each 3. And then now I'm adding, because both of these triangles are above the axis, so this time I'll be adding 1/2, the base and height of this are both 1. So this is 9/2 plus 1/2, or 10/2, which is 5. So that's much better if you happen to have a clean looking function where the area under the curve is a sort of nice geometric shape that's easy to calculate its area. This is one way to handle the definite integral. Okay, so here are some other just facts. So all of these things are true. If you have an integral that starts at 0 and goes to some unknown ending place b, right, and you're taking the area under e to the x, so let me just give a rough sketch of, remember, e to the x looks approximately like this, right, where this crosses at 1. So we're choosing some place b and calculating this area. Well, that's like kind of trapezoidal, right? But there's this like curved edge, so that's not straightforward to calculate using geometry. So we've got an identity for this. Note that it has to start at 0 though, okay? Well, we have a way around not starting at 0 later, which we'll get to in a little bit. But for now, this theorem is only true if you start at 0. This is a more general theorem where, so here I'll come over here and sort of sketch what's going on. So imagine I have the constant function c, right? Like this is at height c. So imagine this is a horizontal line here. And if I start at A and go to B and I want the area under the curve, well, that's just going to be a rectangle, right? And the width of the rectangle is B minus A and the height of the rectangle is C. So this makes good sense geometrically, right? But if you integrate a constant function, this is what you get. And then this linear function is the one that we just did. And that's sort of based on the area of a triangle, right? So if you start at 0 and stop at B, the area of that triangle is going to be 1/2 base times height, but because it's the standard linear function, base and height are both just given by this letter B. This one is less geometric, but it's also true. And you may start to notice some patterns developing here, and if you do, great. That's the sort of fundamental theorem of calculus is going to address some of those patterns. If not, that's fine. These theorems are just sort of, take them as you need them. So let's get a couple of other things, and then we'll work one other type of problem that sort of gets us around the sort of you have to start at 0. Because in a lot of these theorems, right, like you're starting at 0, start at 0, start at 0, but you don't always start at 0. So what's a sort of way around that? But before we get there, let's just also make the comment. In a previous video, we saw that indefinite integrals are linear, meaning you can split them up across sums. I guess I'm missing a parenthesis here. You can split them up across sums, right? If I want the definite integral of f plus g, that's really just the definite integral of f plus the definite integral of g. And similarly, I can factor a constant out. We knew that these were true for indefinite integrals from a previous video. Indefinite is where we don't have the a's and b's here, but just the integral symbol. But it turns out they're also true for definite integrals. And then two other things. One is if you've got the numbers out of order, right? So like if I want the integral from b to a, that's sort of like moving left on the number line. Well, that's not great. And it turns out the sort of cost of flipping those to be correct is a negative sign. So the way that I like to remember this is that if you're moving the wrong way in the graph, you're not collecting positive area, right? If you're moving this way, you're collecting negative area. And if you're moving this way, you're collecting positive area. That's effectively what this says. So if I go from B to A, I'm working backwards, and that should be the opposite, like the same absolute value of this area, except the opposite sign. So for example, if I know, let's just do the integral from 3 to 1 of x dx, right? So these are sort of out of order, right? Like in general, you want the smaller one on the bottom. So then that's going to be negative integral from 1 to 3 x dx. And from the theorem above, we know that, okay, well, we don't know that actually. But if you think about this geometrically, you can think about this starting at 1 and ending at 3. And this is sort of trapezoidal, or you can imagine it as a square together with a triangle on top. So this square, right, will be 2 by... So let's see, 1, 2, 3. Yeah, the square part of this will be 1 by 2, right? And then the triangle part will be 2 by 2, so 1/2, 2 by 2. So then in this case, I end up with negative, right? That's where this is sort of getting carried along for the ride. And then the area of this thing will be 2 plus 2, so -4. Okay, so again, the cost of sort of switching the order of these upper and lower limits is you have to introduce a negative, which I think of as if you're moving the graph across the graph in the appropriate way, you're collecting positive area, but if you're working backwards, you're collecting negative area. And then finally, this theorem, is straightforward, but it also gives us something that is helpful. So all this says is if you've got some interval and you're taking the definite integral from a to c and b is some point in the middle, well, if you want all the area under the curve, right, this represents all of this shaded area. Really, I can choose any point in the middle and then add this part of the area with this part of the area, and I should end up with the whole thing. Right? That's basically all this says, is that I can choose any point between a and c and set this up as two definite integrals instead. Well, this is nice when combined with the results from above. Okay, so one of our theorems from up there said that if I have the integral from 0 to b of x squared dx, that's equal to 1/3 x cubed, or 1/3 b cubed. So I would like to be able to use this, except I'm not starting at 0, right? So that's when I'm going to use this type of result. All right. In particular, what I'm going to do is say, all right, well, I know that the integral from 0 to 5 of x squared dx is equal to the integral from 0 to 2 of x squared dx plus the integral from 2 to 5 of x squared dx. So this is the one that I'm actually interested in, right? But both of these start at 0, right? So now I can use this theorem to evaluate them. So I've sort of put this in context with some other stuff that I do know how to evaluate, and now I can solve this for the unknown piece, which is this. Don't worry, soon we're going to get the fundamental theorem of calculus, which would tell us directly how to calculate this. But for now, we're just sort of like, exploring the idea of a definite integral. So this is supposed to be, right, 1/3 5 cubed, according to our theorem, right? This one is supposed to be 1/3 2 cubed, and then this is the one we don't know. So doing some quick algebra, we can move that 1/3 2 cubed, and it will tell us that this integral should be equal to 125 cubed minus 8 cubed, right? Because this is 8 cubed, this is 125 cubed, and I'm going to subtract that 8 from both sides to isolate this, right? And if I subtract 8, this should be 117 over 3. Well, 120 over 3 would be 40, so that means that this should be 39. So again, this theorem seems like common sense, that you should be able to split, cut this in two and you still have the same total amount. But the reason that we like it, or that it's helpful for us right now, is because a lot of our theorems in this section, or in this sort of point of our calculus journey, they require a definite integral to start at 0. So if you don't have one that starts at 0, you can always sort of set it up like this, where you do 0 to the end, and that's 0 to the original lower limit, and then you'll have your piece left here. So this is a little bit about how to use geometry to evaluate definite integrals, as well as some basic definite integral properties.